Thank you, and thanks for coming to this talk, where we will be looking at how you can create your own skyscapes using volumetric clouds in Unreal Engine. So the volumetric cloud system in Unreal, it's a custom rendering solution that has some really nice physically based rendering models and approximations to get some realistic looking clouds. And the nice thing about it is that you can use all your standard material based tricks and knowledge to sculpt the cloud shapes. And it's also ray marched through the sky using a very fast algorithm, so you can get some nice results, and it renders quite fast. So all of the heavy lifting is done for you. You don't have to code your own HLSL for loops or anything. It's all kind of right there, and you just use your standard material system that you know to get your results. I'm Elliot Jones. I work on the Fortnite technical art team, and I live here in Wellington, New Zealand. So I love creating procedural and sort of simulation-based systems in Unreal to create worlds and make realistic-looking things. And in this talk, we're going to be looking at the cloud system itself, its components, how you can interact with it, and how you can sculpt your clouds using things like volume, textures, and noise, and how you can approach optimizing the system as well. And just a bit of a disclaimer, I'm a technical artist, so this is a technical talk, so hopefully that sets you up for what's coming ahead. And when you open up Unreal Engine and load up a default map, then there is a default volumetric cloud actor in your level. And that's there so you can dive in, have a look around, see how the material is set up, and you can go in and start playing with it. But that can be quite sort of daunting from the get-go, and you might not know how to pick it apart and see how it works. So you might want to go in and start playing with parameters. But even before that, like, you might want some fundamental understanding of how it actually works, so you know what these sliders do. So at the heart of it, it's a ray marching algorithm that for every pixel on the screen, we start from some pre-described height in the sky, and the system will take these ray marching steps through at regular size steps and sample a density field. And at the end of the day, it will keep going until it hits some pre-described height, and it will terminate. And we use these materials to describe what that density value is at each point in space. So what will happen is, at each ray march step, the position will be given to you in your material, and it's your job to go through and tell Unreal what that final extinction value is, so that it can actually go back, be accumulated with the rest of the samples, and finally reach your camera or the eye, and you get a final value for your clouds. So let's do a really quick setup and see how this kind of works. And I've broken it down into stages so you can kind of see what steps you'd need to take. Because it's nice to create something quick and dirty and get our kind of appetite wet. So here's really, really basic material. And again, we're trying to tell Unreal what that extinction slot is. And then we come back to the fact that clouds, what are they? They're just water droplets suspended in the air. So light travels through clouds, it's reflected, refracted, scattered, and absorbed. And we're just telling Unreal how much is there. And the rendering system will calculate the shadows and all of the kind of physical values for you. So here we're given the world position at the point in the ray marching stage, and we want to fit a UV value so we can sample some textures. And that means taking world position and mapping it to a 0 to 1 UV value. So here we have our source UVs, and that can be visualized quite easily just as a span across the world in X and Y. And then we have these 3D textures which we will use as the basis for our rough cloud shapes. So we sample our texture, and then we want some way to kind of control where the gaps are in the sky. Because if we have a completely covered texture with values everywhere, we're going to be getting quite a gray, overcast sky. So we want some way to kind of cut holes in these textures and make it so that there are kind of bits where we can see through to other clouds. And one a quick way to do that is use the contrast node just to kind of create those gaps. And the next stage would be to kind of state what the actual kind of thickness of the cloud is going to be like, so that we can kind of control how dense it is and its overall look. And that can be as simple as a standard kind of multiplier. And then another stage might be to control the actual kind of edge quality and how soft it is, because that's going to dictate your mood, your style, that kind of thing. So those kind of things can be done with ramps and gradients, which we'll get to in more detail soon. And then there's further, more advanced controls that the system gives you in the material editor that will let you control more physical values to kind of control things like the way that the light kind of scatters based on the incident angle, that kind of thing, which in this case could be a whole talk on its own, but we're going to kind of skip through some of this and look at the more kind of practical side of things. So let's dive a bit deeper. And when I'm encountering a kind of a complex system like this, I like to delete everything and start from scratch, because then I kind of get a better understanding of how it all works. So I delete that actor, create a new volumetric cloud actor in the scene, and what you get is this actor in the scene with a single cloud component, and there's all these settings on the side, which can be quite daunting. So we're going to be going through these. Now the next thing you need is a material, because that's going to be what is going to be dictating the look of your clouds. So you create a new material. And just the practical setup of this is that you have to set it to be in the volume domain, and you have to set its shading model to be additive, and optionally turn on some usage flags so that you can just get it to work. That's just the practical setup, so no need to kind of memorize this or anything. And then we take that material and we drag it onto the cloud actor, and we're good to go. We have a blank setup. Nothing at the moment is plugged into that extinction slot, so we're getting no clouds. And one thing you can do to really make your life easier is to enable the Volumetrics plugin, and because it comes with lots of volume textures with it. So this is shipped with the engine. You just need to enable it, and suddenly you have all of these volumetric textures available to you. So I like to pick this one as my kind of starting texture. This is a volumetric texture which has a basic kind of Voronoi pattern to it, which will get you a lot of the way there. And that's roughly what this kind of looks like. And 3D textures, all they are is the same as 2D textures, but they just have an extra dimension. So you can sample it with your standard UV, but there's also a W coordinate that you can index into it. So mapping that world position to a UV value between 0 and 1, that's where we kind of use just standard kind of division. And here we can just use some simple scalar parameters to tell Unreal how big you want that kind of scale, how big you want that UV value to kind of tile over space. And the Unreal engine actually ships with some handy conversion from centimeters to kilometers for you, just so you're not dealing with massive numbers with lots of zeros. And here we have that visualization of the UV space spanning your world, but you also have this Z height value as well, because it's world position X, Y, and Z. So we can actually use that to index into the texture in height, but we'll also see later how we can use that for more creative effects. And if you're having trouble kind of visualizing what that tiling value is doing to your kind of index sampling space, then one thing you can do is actually plug the UVs into the albedo slot of the material editor to kind of see that tiling value happen, because it's just a fractional repeating value, and that helps you kind of set up your clouds in context from the camera. So yeah, let's sample that texture and plug it into the density slot and see what we get. Okay, well, if you want to render some overcast clouds, then this is the good way to go about it. You might be thinking, well, this isn't so great, where's my clouds? And that's where we come to that idea of creating contrast and coverage to kind of sculpt where the clouds are. So adding that contrast node means we can create those gaps, and then suddenly we kind of start to see the clouds taking shape. But we're not quite there yet. We need to do a little bit more. That's where we start adding those advanced nodes to tell the system all of those kind of physical parameters, so it knows how to create shadows and scatter the light internally, so you get nice kind of sort of bloomy lighting, that kind of thing. And that takes it from this to this. So we're starting to see a cloud system that is looking more like realistic clouds with shadows. But it is looking a bit sort of fizzy. So that's where we want to control that density value. And you might be thinking, well, what values do we put? How much do we multiply it by? And that's where we come to the actual kind of units themselves. Like typically, density is a volumetric unit, which represents how much stuff is in a region of space. So I just did some searching on the internet and randomly found this value of 0.5 of a gram per cubic meter. So I put that into the Unreal, and that takes it from this to this. So again, this is an approximation, this rendering system, but it was nice to know that I could plug in a value that I found that was a realistic value, and it got me within kind of the rough ballpark of what I was going for. This was a placeholder title slide, so probably should have taken that out. But the challenge here was that I'm sampling a 3D texture, which is repeating in the XY plane, but it's also repeating in Z. But what's happening is that the rendering system, because it renders from that sort of bottom layer, we're kind of indexing straight into a texture, and we're getting kind of a clipping of that texture. So we want some way to kind of have some gradation and ramp off that bottom of the cloud. So this is kind of a rough representation of what we want to happen, is to have a ramp that is 0 at the bottom and 1 at the top, so that when we multiply it, we get less density at the bottom, which in the end will result in a softer looking cloud. But how can we access a 0 to 1 ramp from the volumetric cloud system? Do we have to do some kind of top layer, subtract bottom layer, and divide by height kind of renormalization? Or can we just take it from the engine, because it just gives it to us? Well, this is what I like to do, is just use it because it's there. This is a 0 to 1 value, which goes from the bottom layer to the top layer. So we can actually just plug it in, multiply over the top of everything, and that will take you from that kind of clipping value to something which doesn't have that flat artifact at the bottom. But it might be a bit aggressive. You might want to actually kind of ramp it in a bit slower, so it's not such a sort of harsh, sort of soft fade off. And you might be wondering, well, how can I now visualize the height of the clouds? And I like to use this test pattern, which allows you to kind of see, again, how high things are from the bottom to the top. And that will allow you to use things like power curves to ramp that 0 to 1 value. So it's not just a linear ramp, but you actually have some kind of fading into it. And it might be a bit hard to kind of visualize what that ramp is doing. So some things I like to do is kind of flip it on its side, so you can kind of see that the ramp isn't so linear, it's more of a kind of tightening on the bottom. So you can play with that power curve and actually ramp your sort of cloud bottom to be a bit softer. So that takes it from what we had before to this, which has a bit more definition on the bottom there. So let's look at some of those settings on the cloud actor. Here's our cloud actor, and we have this kind of top section which controls those layer heights, where they start and where they end, and actually how far away we're going to be tracing. Then we have our slot, which is where we plug our material into. And then we have a section at the bottom which controls things like how many samples we're doing, how many shadow samples. This is generally a kind of performance quality trade-off section. So yeah, that layer height is how many kilometers from the ground we're going to be starting our sort of ray marching algorithm from. And then the layer height is going to be the sort of height above that at which the ray marching stops. So what do we choose for our layer heights? We have all these different types of clouds at different heights, which go all the way from, sort of here it says, like 1,000 or 2,000 meters, all the way up to 12,000. If we put in sort of a layer height of 1,000, do we need to have a 12,000 layer end height? What do we do? Well, one thing I did is I went on a walk near where I live, and I noticed that there were some clouds kind of hitting the top of that mountain range in the distance. So I thought maybe it's a good idea to kind of see how high that mountain range is. So I kind of found on maps where roughly that mountain range was, and I lined it up and kind of verified that that was the actual mountain. Then I can actually look on the maps and see how high it was. So in this case, it was 800 meters. So I plugged in 0.8 kilometers into the cloud system, and that got me this, which again, doesn't look amazing off the get-go, but then I realized that the tiling value is now off off by a way because we've kind of reduced that height. So basically I change that tiling, and that kind of brings us back to this, which is, again, in the rough ballpark of where we want to be. So it's a bit thinner, it's a bit sort of less dense, and that's because the layer is much thinner now. So what we do is increase the density, and that got me this. So getting closer, but it's still looking a bit weird now. Now there's kind of lots of dark patches, and that came down to the fact that there's this tracing distance parameter on the cloud actor node that lets you control how far the shadow tracing, how far that shadow tracing sort of goes to occlude the clouds. And if I reduce that to kind of match the sort of the scale of the clouds that we're trying to achieve, then that basically distributes those samples across a smaller area and gives us higher quality. So this is getting closer to what we want. So now we have our rough cloud shape given by that 3D texture, and we want to kind of add some actual kind of details to these clouds. So what we normally do is use another tiling noise texture to kind of erode holes in the clouds. And we can multiply or subtract holes, doesn't really matter. As long as you stay in that kind of normalized range between 0 and 1, before you have your final density multiplier, you can actually kind of subtract or multiply, up to you. And that's roughly kind of represented here with this image, where we're just kind of multiplying and sort of picking holes into the clouds. And what I like to do is have a separate kind of UV scale sort of remapping for the details, so that you can control the size of the main clouds and the size of the detail separately. And again, that's just a multiply node there. So what we would do is we'd sample our main clouds on the top, and then our detail sort of clouds on the bottom, and then subtract that from the main clouds. And I've got an extra kind of detail erosion parameter there to control how much of the clouds are actually subtracted. And that gives us something like this. So what I'm doing here is animating what we had before with the detail erosion cloud, so you can see how it's kind of eating away there. You don't have to use 3D textures if you don't want to. If you're targeting a platform with kind of, lower sort of memory sort of requirements, then you can use a 2D projected texture where you're just kind of projecting down and feeding that into the density extension slot. And then what you could do is use fall-off curves to kind of ramp off the top and bottom. So what you would have is a 2D texture projecting down here, and then what you'd want is some kind of ramp now that fades off that top and bottom, where it's sort of full density in the middle and then falls off in both directions as you go away from the center. And a nice little mathematical equation that does that is a nice kind of squared function. So you just take a kind of a linear ramp and square it. But you kind of want it to be centered. So what you do is you do some math to kind of recenter your sort of linear gradient. You can absolute that to kind of create this triangle shape. Then you do a 1 minus to flip it vertically. And then finally you can square it to get that kind of sort of round kind of profile shape. And again, if you look at it sideways, you can imagine that's like a cloud profile. And you can wrap that into a material function and hand it around, and everyone can use that. So here's just that visualized, where on the left column we're seeing sort of a linear ramp, and on the right hand side we're seeing more of a sort of soft ramp. And the engine actually ships with some nice handy nodes in the material editor for you to kind of visualize those functions as well. So here we're just visualizing the triangle function and then the square function. So what we do is we sample our linear gradient, run that through our material function, which we just made, and then we get the soft tops and bottoms there. And that's our rough cloud shape, which when we add noise on top can give you something that, again, looks a bit better if you're careful with your noise and is a bit cheaper to run because we're not using full 3D textures. So erosion isn't the only thing we can do. We can actually warp the input space using vector noise, which instead of eroding the sort of noise after you've sampled it, what you do is you sample this 3D texture, which distorts your world position before you even sample your main clouds. And this kind of borrows ideas from fluid mechanics, where you advect fluid through a field. And that gets you nice little wispy details like this, where instead of kind of cutting holes, you're pushing and pulling, and you get little nice kind of curly wisps. So again, you have your own separate sort of remapping value, which will map your sort of main world position, which we're just getting into this detail vector UV space. We then sample the vector value, and then we're going to subtract that from our world position. And that will get us a new distorted UV space, which we then use to sample the main clouds. And then that will give us something like this, where you can kind of see it being pushed and distorted from where it was before. And again, this is kind of the same, but at a kind of much kind of lower frequency, higher amplitude level. So you can see it being pushed around. And you can do both. You can actually warp and erode at the same time. And there are other ideas like using volumetric displacement, where what I just showed you was a vector noise distorting UV space. This is actually exactly the same thing, whereas what we're doing is we're doing this in 2D now, where we're covering a much wider area. So each color there represents a direction, and we're just going to kind of project that texture in 2D. And what we get is something like this, where we can actually distort and warp on a much larger scale, which is great for kind of more stylized effects. So you can get these kind of much larger brush stroke type clouds. And you can kind of adjust that kind of amplitude to taste to kind of get different stylized clouds. And this is just showing that kind of amplitude kind of being animated, so you can kind of see its effects happening in real time. So this just shows how we're sampling that volume, that sort of projected 2D texture. Then we're subtracting that from the world position here, and then we are doing another sort of detail scale on top of that, and having 3 separate UV spaces. Now we have 2D displacement and 3D displacement. What we can also do is do vertical displacement to kind of create like a height field sort of cloud system, where what we're doing here is we're sampling that 0 to 1 normalized ramp from that cloud sample attributes node. And what we're doing is we're just subtracting a sort of 2D projected noise, in this case just a kind of a cell noise. And what we do is we figure out if we're above 0 or below 0 based on this sign node, so if we're positive or negative. And what that does is it basically distorts in the vertical direction, so you can get these kind of like rolling cloud effects. And this kind of thing you can actually combine with other methods as well. So you could combine this with 2D warping and 3D warping, whatever you want. And if you're doing something like that with vertical displacement, it's usually best to have kind of smooth noises, so you don't get any kind of jumps in the vertical kind of space next to each other. So yeah, just be careful with when you're doing vertical displacement. So now let's get on to how we can control some of that coverage. So before we were using a contrast node to kind of create gaps in the clouds, which was nice, but it was a bit brute force. So remapping is a kind of a common operation in the tuck art world, where we want to take a pre-described range where we know the input and output sort of upper and lower sort of bounds, and kind of either kind of stretch that to a bigger range or kind of squeeze it into a smaller range. And what that will allow us to do is take in a sort of a texture which we know is between 0 and 1, and sort of pick 2 values where we want to kind of set as the new minimum maximum. And what that will do is it will basically allow us to kind of cherry pick a range within a texture to kind of dictate where we want the clouds to be. And the nice thing is that it retains all the values in between as a linear relationship. So we get kind of a much nice, we get a lot more kind of softer edges and that kind of thing. So we're not getting a kind of a hard contrast cutoff. And that's quite nice because we can actually make this dynamic, where we can actually run this in a game or other type of content where we have this kind of changing value. So this could be used in a weather system in a game, or some other kind of mechanic that responds to gameplay. So I've been showing all of these kind of material tricks and ways you can control your clouds. But that's kind of one half of the equation when you're trying to achieve a look. The other side is that the actual atmosphere system in Unreal works in conjunction with the clouds, and they're designed to kind of work together. So there are a lot of controls to control the scattering in the atmosphere cloud system, or the atmosphere system. So we can control things like the me-scattering, which actually is due to kind of particles in the air, and that will give you very nice kind of overcast looks. And there's the scattering, and there's also the absorption. So the scattering will kind of get you that overcast look, and then the absorption will kind of give you kind of a general attenuation. And if you are doing this kind of me-scattering overcast look, then when you're combining it with your main clouds, I just recommend to kind of go with more of a softer edge to kind of tie it all together, because it's really trying to represent kind of, moisture in the air, and you kind of want it to all be in the same system. Then there's another kind of scattering, which is the Rayleigh scattering, which I like to think of as the more artistic kind of control, because it's due to particles in the air which actually kind of change which wavelengths of light are absorbed and scattered. So depending on which particles are in the air, you'll get different colors, and you do actually get some kind of artistic controls on the side there for changing which colors get absorbed and scattered. So this kind of scattering reminds me of lots of old J.M.W. Turner paintings. So if you're going for that more stylized look, that might be the kind of thing you want to play with. So that allows you to kind of get really nice sort of evening sky effects and sunsets and that kind of thing. And just be careful with the scattering settings, because if you are going for these kind of like low sun angle effects, the scattering can actually attenuate the light quite a lot. And that's because of if you imagine that you're at the top of the planet and the light is coming from a low angle, it's got more atmosphere to travel through, so it's going to scatter more and kind of they'll get less light. Whereas light coming from top has to travel less through the atmosphere, and so will kind of reach you with less scattering. So we have all these kind of cloud systems with 0 to 1 values that we're remapping to control where the clouds are. But what if we have multiple cloud types that we want to composite into one thing? So we have all these different cloud types that are at vastly different scales, and we have one actor, which with this one 0 to 1 space. So we've got these cumulus and stratocumulus and stratus clouds that your everyday clouds I like to think of. Then we have our big cumulonimbus, which are kind of the big kind of ominous things that kind of take up the sky. Then you've got the ones which I like to call the other ones, which are the general weird ones that you see with lovely kind of odd patterns and make you wonder how they were created, that kind of thing. And those last ones I'm probably not going to be talking about today, but they're so high and so thin that they're probably best dealt with as a sort of skybox texture that is just rendered on a flat plane or something like that. So I'm going to concentrate on the other kinds of clouds, the ones that you see more with parallax and sort of shadow effects, sort of more near to Earth. So yeah, the big challenge is how do we get all these different cloud types and composite them together in one space, because we only have this one 0 to 1 space to work with. So what we'd like ideally is to have like a mini 0 to 1 space at one cloud height, another 0 to 1 space at another, and then maybe a third one, and we want to composite them together. Well, we just come back to our remapping trick where we can actually just feed in the ranges that we want from that 0 to 1 and just tell it which levels we want to kind of pick from. So ideally we want to take it from this and cherry pick that area, and then we can run that through some kind of like layer mask sort of fall off ramp to get that thin layer. And we can do this as many times as we want, where we can sample from 0 to 0.1 and then from 0.1 to 0.3, and what we get then is kind of the system where we can visualize these 3 separate layers and pick which heights we want to render clouds at. And this is just another test pattern that I like to use to kind of visualize that. So we have these 3 layers, and we know where we want to put things. How do we get clouds in there? So one way to do it is to use noise. Another way is to use sort of DCC apps to generate cloud shapes for us. So I like to use Houdini because it's got these really nice kind of cloud modeling tools built in there. Someone's already done the hard work of making these HDAs to do that for you. So you can actually just create a rough sort of cloud shape and then use the nodes, which I like to use the secondary shapes option there in Houdini to generate these kind of nice spherical kind of scattered shapes there. And then we use the cloud noise node to add all these details, which has its own kind of advection and warping and baking built into it. And then we can bake that out as a texture and then import into Unreal. And for different types of clouds, you just use a different kind of base shape. And again, go through the same thing of scattering shapes and using the noise node to give it noise and exporting. And then what we can do is we can import it into Unreal, and we can choose which height we want to render it at using remapping, and composite them together either by adding or doing a max, or whatever operation you want, and just feeding that all into the extension slot. So one of the challenges is how do we get like a whole skyscape full of clouds? Because when we're exporting from Houdini, that's quite a big sort of memory requirement to export out high resolution textures. And there are ways to do sort of cloud and noise generation. One of them is just to import a texture you already have, or you do what I just showed, which is just generate them in Houdini, or we can actually generate them in the engine. So if you have a texture, just import it. And there's a bit of a difference when you import a volume texture into Unreal, where you kind of have to import a sort of 2D atlas, and then you have to right-click it and choose this Create Volume Texture option, and that will actually kind of build the 3D texture for you in Engine. Actually, in 5.3, there's a new VDB import option, which allows you to import sparse volume textures. So that's the new SVT system. So I haven't got any slides for that in here, but I've used it and it works. So if you do have VDBs you want to import, then I think 5.3 you should give it a go. So we import that 3D asset, and if you want to know more about that, there's some blog posts here for you to kind of read over, and it'll tell you how to generate those textures and import them. So then we can actually author noises and volumes in Houdini. There are actually the side effects labs nodes are there, which actually create that 2D atlas for you, and then you can just import that into Unreal as usual. Or you can do things like generate them in Unreal Engine yourself, again using just volumetric materials, and then you can actually write to a render target and then right-click that and convert it to a texture. Or you can do things like create editor widgets, which are custom blueprint actions, which I won't go into detail here, but here's one I just made that's really easy to make, that you just, basically you're adding your own sort of engine tool to be able to right-click on a material and export a 2D texture. So that brings me on to signed distance fields, which are sort of one of my favorite things. A signed distance field is basically a volume. It's the same as a density volume, which all it does is it stores a value at every point in space. It's just that instead of a density value, which sort of stores how much stuff is in space, it stores a distance value to some surface. And that's a bit of a weird sort of concept to get your head around at first, but really this is one way to visualize it. It's just this surface is where in the volume texture the value is 0. So 0 means that you're on the surface. If the voxel contains a value that's, say, 1 or 2, that means that it's outside the surface. It means it's 1 or 2 units away. And if it's negative, it means it's inside the surface. And this is it kind of visualized, where what I'm doing here is just kind of visualizing as it gets darker, that's going further inside, and as it's getting brighter, it's kind of going outside. I've actually remapped it so that 0.5 is the sort of central reference point, and that makes it easy to export and import into Unreal, because textures kind of, it's easy if you keep your texture 0 to 1, and I'm just choosing 0.5 to be the level at which the surface exists. So here's just another kind of representation of that, where we're seeing those negative values inside and positive values outside. And you can just imagine that these textures represent these kind of little mini one-dimensional ramps that go away from the normal of the surface or inside to the inside the surface. And that's nice because it's a one-dimensional kind of ramp. Conceptually, we can remap that itself to kind of control where the density is. So here we can say the negative values, which in this case are going to be the 0.4, which is below that reference point, is going to be like the inside of the cloud, and then the outside of the cloud is going to be 0.45, which is kind of further away. So that essentially allows you to turn a distance field and convert it into a density field. And that's one way to kind of get these kind of shapes into Unreal. Another nice sort of benefit of that is that you can actually add to and subtract from these distance fields. So they basically give you a bit more flexibility than density fields, which are actually kind of fixed in place. Whereas here you've got some sort of variation where you can kind of contract and expand them. So here's it being sort of visualized where we're adding to a distance field, which actually shrinks it, which is kind of a bit counterintuitive, but when you kind of work it out, that actually is happening. So another nice benefit is that because it's a signed distance field, you can actually kind of control the softness of the edges simply by picking where those min and max values are. So that leads me on to how we can kind of make these clouds render faster. In Unreal, there is this conservative density slot. And this is a really powerful thing, which basically is a way to tell the cloud system where density is and where it's not. Because if we plug in a value of 0 there, then every time that sort of remarching algorithm sort of propagates, if it detects a value of 0, it can basically skip a whole lot of empty space. And then when it encounters a positive value based on some threshold, then that's going to basically evaluate the full material. And you can choose where in space you want to actually spend the cost of evaluating the whole material. So you can kind of visualize it like this, where the green section is skipping lots of empty space. And as soon as we encounter some density, that's where we want to take kind of smaller steps and incur the cost. And this is actually a float 4 value. So I'll be using this to actually kind of pack along some data along for the ride. And we'll see how we can use that for optimization soon. Yeah, that's saying all that stuff. So then once we've plugged that value into the conservative density slot, when the full material is actually evaluated, we can actually extract that value from this advanced input node. And that will allow us to kind of sort of reconstruct that material and pick up from where it left off. I know this is it's a bit of a hard concept to get your head around, but this is actually very powerful because what it does is it lets you kind of plug in things like signed distance fields into that conservative density value and do cool things with it. So if you want to visualize where your cloud is rendering, you can turn on this CVAR flag, and basically you can see where it is rendering and where it isn't, where the green is actually the kind of full material evaluation and the red is kind of where it's skipping. So yeah, we can stuff whatever data we want in there. So in this case, what I'm doing is I'm sampling the signed distance field. I'm using a sign node to detect whether we're inside or outside of the cloud. If it's inside, that's going to be a value of 1, and we're going to plug that into the conservative density. And if it's outside, then it's going to be 0, so it's going to skip. And then we have our raw distance value up there. So what we do is we get our raw distance value, plug it into the second channel of the conservative density, and that's going to be available for us on the other side. So we have a conservative density, which is that cheap, very rough sort of value that controls where the clouds are, and the distance value, which we can use to reconstruct. So we unpack that distance value, and we're using it now in the section of the material which is being run at a higher cost. And from there, we can do things like add to the distance field using noise textures to erode into it. So that way we get like a very nice cheaply evaluated material right up front, and then all of the sort of noise textures are happening down the line in the sort of more expensive bit where we want it to happen. And here you can kind of visualize the red section where it's kind of skipping through, and the green section where it's actually evaluating the noise. So then we can do things like create these vast sort of tiling textures in SDF sort of space where it would be quite high cost to develop and create density textures because your resolution is basically being spent in encoding all that detail into a density texture. Whereas now that we have this distance field, we're getting a bit more sort of bang for our buck. And that means we can have these kind of quite large tiling textures that repeat, and we have a lot of control over where we add detail. They can expand still. We can control the edge softness using this distance field, and it's kind of a really nice kind of way to work with volumetric data. A few little tips when we're sort of working with the cloud system, which is that when we are using a lot of low sample counts, so if we're trying to make this faster, one thing you can do is actually lower the amount of samples you're doing so that your sort of ray marching steps are taking larger distances. What you can do is get a lot of fizz and noise, and that's because Unreal does what's called the sort of temporal sampling to, over time, take lots of samples with lots of jitter offsets and then kind of combine them, which most of the time works really well. But sometimes if you do too few samples, then you will see this fizz. And some things you can do to mitigate that are do more samples, which you might not want to do, or you can reduce the contrast of your clouds, which kind of masks a lot of that kind of noise. Then there are these two kind of CVAR values you can put into the engine to tell it more about how many samples you want to do. So we had those sample controls on the actor, but this gives you more finer control over the quality. So the V-Ray max sample count, or sample max count, will actually dictate how many samples you want to do. So you can increase that to get more samples. And then the distance to sample max count, that's a bit of a weird one to get your head around as well, because that's actually a distance in kilometers over which those samples are kind of distributed. So you're telling it that over 15 kilometers, you want to do 768 samples. So in effect, what's happening is that you're entering your sort of cloud layer, and if we kind of zoom in a bit, we're kind of saying that over that 15 kilometers, you're doing, say, 512 samples. But if you set that distance value to 25, then your step size is going to be calculated as being larger. So that distance to max sample count, in effect, is a kind of a normalization factor, which kind of tells you that distribution. So depending on the scale of your world, on the size of your characters, or whatever kind of style you're going for in your game, you want to fit that distance scale to the kind of scale of your game appropriately. So here's the kind of the default value of 15, and if we lower that to 2, then that's going to basically make our step size smaller. And I find that a much nicer way to kind of manage the performance. So if you are kind of limiting your tracing to a certain distance and setting that max sample count to a specific distance, then what you can do is you can actually use these kind of 2D cards to kind of fill in gaps on the horizon. So here what I'm doing is I'm using a 2D kind of height map, which represents a cloud, and I'm using a node that exists in the engine, which is the Raymarch height map node, which actually calculates 2D shadows for you based on a 3D sun direction. So what this node will do will take a sort of the 3D sun vector, transform it into tangent space, which basically turns it into a kind of a flat 2D vector that makes sense in the context of the sort of the 2D card. And it'll actually do some volumetric tracing through that 2D card for you. So what you can do is end up with something that you can fill in that gap at the bottom, and this is a very rough, quick example, but you can see it alongside the volumetric cloud system, and the shadows kind of update dynamically. And if you're careful with all of your kind of scattering settings and the color of the distant clouds, you can actually get that to kind of match up quite nicely if you want to. So that's a massive optimization, which means that you're not rendering far into the distance just for a small area on the horizon. You can actually sort of concentrate all of your samples close to camera and get the highest quality, and then fill in on the horizon where hopefully not many people are looking. So yeah, general kind of tips when approaching sculpting your clouds is to try to avoid anything that's too repetitious, that has the same quality everywhere. Try and change your softness over space and your edge detail, and try and just break things up as much as possible. And then use the sky atmosphere as much as you can to kind of tweak those scattering settings, because just even a little bit of scattering here and there can really kind of just subtly make things look a lot cooler. Keep texture sampling to a minimum, especially when we have vector textures that then offset UV space, that then sample other textures, because when you're sampling textures that are dependent on other textures for their UV space, that introduces a lot of latency on the GPU. So if you're doing that, try and keep your sort of vector displacement textures quite small, because that's better for sort of GPU cache-friendly performance type stuff. And yeah, decide on kind of your world scale and fit your sort of your distance values and your sort of CVAR values to fit that world, and really target where you want to render in screen space. So yeah, my kind of points for this are that you can just start going in there and creating materials and sampling noise and distorting, and it's quite fun. I mean, we get really nice clouds here in Wellington, so I'm kind of inspired often to go in and start making these really nice kind of beautiful wispy looking things. And often the kind of the simple approaches are the best ones, where 80% of your look is going to be determined by some nice texture that you find. So don't try to overdo it. Just be careful about where you're sort of picking your sort of height ranges and that kind of thing. And yeah, if you want to use sign distance fields and are comfortable with that, go for that. But you don't have to. If you just want to create some beautiful looking textures as in Houdini, export them and use that, that's fine as well. And go outside for walks, because you know you'll be inspired, and you'll it's really nice to kind of link what we're doing in the computer with something that's right there in front of us outside. So yeah, I enjoy it. Thanks for coming. If you have any questions, then fire away.
Hi, thank you very much for the talk. Just out of curiosity, what's the support like for the camera being at level to these clouds or inside the volume?
If you're inside the volume?
Yeah, what happens to the clouds at that point when the camera's moved inside?
It does work. I think you have to be careful about what you're sampling really close to camera, because if you're flying through it, suddenly the textures that you're sampling are kind of, you know, covering a much wider area of the screen. So you might want to have some system where you're kind of blending in a higher detail texture as you're going, because it's going to be very blurry at that scale when you're kind of right full screen. As far as I know, it works okay. Yeah, I mean, Fortnite starts with someone falling through clouds, so you know, it tends to work.
Are there any online resources in the Unreal Learning platform, or I don't know, like somewhere else, about the exact steps to take on the Houdini to Unreal workflow?
Yeah, I mean, there are quite a few pages in the documentation which take you through a lot of those kind of CVARs and that kind of thing, and how the rendering system works. So that's kind of some good technical documentation there. There are quite a few tutorials I've seen on YouTube. And again, those blog posts that I put up there are really good for figuring out how to author 3D pseudo volume textures. The Unreal sort of dev community hub is a great place for tutorials and courses.
One of the things on the screen was to keep it simple, right? So I was thinking, what if I want to create hurricane 4-minute tornado? Would it be possible to keep it like playable and like animated sort of thing, like in at least at some level?
Yes. So one thing I've done before is to use sign distance fields, but generated as a material function. So I created a torus procedural analytic shape, and use that to kind of sample a 3D volume texture that kind of had, you know, like animating inwards, that kind of thing, and twisting, that kind of thing. So I would use like some kind of cone SDF with a sort of rotation as it goes up in Z to get that kind of thing. It's definitely possible. I've done it. Yeah, I'd love to talk more about that, but yeah.
Yeah, I should try that. Thank you.
Yeah. Okay, thank you very much. Cheers.
Cool. So from here, I invite you guys to head on downstairs for the closing keynote.
Cheers, man. Thank you.